Welcome to the next of our series of mini-lectures. Today we're going to cover ray matrices, which is a mathematical method for describing the propagation of rays of light. Now remember, our ray description of light says that individual particles move in straight lines unless they hit a boundary of some type, provided that the things they interact with are much, much larger than a wavelength. So this theory is really applying to macroscopic lenses and things on the orders of hundreds of microns, millimeters, or larger. And a boundary, of course, is defined to be any surface where there's a change in the index of refraction. And it's called the ray description because a ray is a geometric line, and it's the straight line the particle of light is going to move along. Now, if you remember from way back in elementary school or high school or whenever you learned about these things, we have an equation that describes lines. It's pretty straightforward. Y equal mx plus b. And we see that, in fact, there are two numbers that describe any line. One, of course, is the slope, and the other is the intercept. Of course, to define an intercept for a straight line, you have to pick a point in space. And so I'm going to define a point in space as this line D, an x value. And let's take the red line first. This right here is the intercept. It's how far below the axis of propagation the line is at that point. And of course the slope is just the run over the rise, and is essentially given by the tangent of theta, where theta is this angle right here. And this is all very basic geometry concepts. You should understand this pretty well. What this means to us is that there are two parameters to describe any line. One of these, in the formalism of ray matrix theory, we're going to call r. And r essentially is the distance above, or in this case below, or in this case above, the axis. So let's put some colors in here to make this pretty understandable. Go ahead and define r right here for the red line, and r prime for the red line is the slope. So r is the intercept and r prime is the slope. So r prime and r is the notation we're going to use. And then just to make sure you understand this, let's define it for the green line. Here's the r for the green line. And of course r prime is equal to 0, since the slope of that line is 0. Now, the way we define a ray in the ray matrix theory is through these two numbers. And the ray matrix theory applies to optical systems. And of course, what we're interested in is thinking of the propagation of these lines through some kind of optical system. And in fact, if we look at the optical system as falling simply between the two lines, an optical system being the space D, from this line here to this line here, it's fairly easy to calculate what the ray's doing for that space. And so let's think of ignoring what happens inside our optical system. We'll think of having a black box. And so the rays come in at some input plane and come out at some output plane. And we want to, using ray matrix theory, describe the relationship between the input ray and the output ray, in the case of the green ray, or the red ray, or any other ray we want to talk about here. So let's take the red ray as a slightly more interesting example. Well, this is a fairly easy calculation to do. We know that essentially the amount of the change in r, so let's have r in here, which is going to be a negative number, and we'll say this value is r out. We'll know for propagating through space with a line going straight that r out equal r in plus the distance d times the slope of the line. And we know the slope of the line that comes out is unchanged from the slope that goes in. And so these two equations pretty much describe propagation of a line through a length of space d. And we can formalize this in a matrix approach through this. If we look at the top equation, remember our array matrix multiplication, we know that the first row of the matrix is going to be 1 because we have the component Rn. And we need to multiply the slope by a value d, and that's going to give this equation. For the second equation, we want to have a 0 here because the position coming in doesn't affect the slope, and a 1 here because the output slope is the same as the input slope. And this essentially is the ray matrix theory. And you can derive ray matrices for lots of different optical elements. I just derived it for free space here. And the ray matrix for free space, or length of free space, is given by this. And we often call this the ABCD theory because the elements of the matrix representing the length of free space are given the letters A, B, C, D, and we'll see this over and over and over again in this class.